problem in compressible, non-relativistic fluid mechanics, but the mathematical techniques that I'll discuss give a beautiful illustration of ideas from mathematical general relativity being imported into fluid mechanics, giving us some new insights into the behavior of fluids. Okay, so as I said, non-relativistic compressible Euler equations in 3D. One big thing to note is that these are not irrotational solutions. There's vorticity and entropy allowed to be present. And I want to point out that there's a parallel theory for relativistic Euler equations. And in the last day from Jonathan Luke, you'll see an application. And so the focus of the talk is going to be on solutions that have very regular initial data, C infinity if you want, but they lead to the finite time formation of a shock singularity. And the techniques that I'm going to discuss are apply in many regimes, but I'm going to focus on a specific regime because it's one of the simplest one can treat. And that's the regime where you take plane symmetric, isentropic, simple solutions. I'll explain what those are in more detail. And you perturb them outside of symmetry and you study the flow. Okay, so that's the regime I'm going to mostly focus on. And the main goal is to construct the maximal classical development. And so I won't be able to construct the whole development today, but I'll construct an interesting piece of it. In fact, constructing the whole development is an open problem in essentially every physically relevant regime. There are two pieces that I really want to talk about. The singular set, this is the set of points where the fluid's gradient blows up, and the Cauchy horizon. The Cauchy horizon is a null hypersurface that emanates from a codimension 2 manifold that can properly be thought of as the correct notion of a first singularity in this context. So I'll explain all these things and show lots of pictures. This is just kind of a warm up for the talk. Okay, and a particular interest in the way that we're doing the problem is to set up the shock development problem. So this is the problem of continuing the solution after the singularity forms. This problem is open in full generality. It has been solved under some simplifying assumptions, famously by Christodoulou. He solved what's called the restricted shock development problem, where he solved sort of a mathematical problem that's not quite Euler, because he threw away entropy and vorticity. I'll say more about these things later. So let me very briefly introduce the equations. In Cartesian coordinates, the usual coordinates, the equations are the unknowns can be thought of. I mean, there are many ways you can set up the problem, but we find it convenient to choose the unknowns to be the density, velocity, and the entropy scalar little s. There are many ways to write the equations. You can write them as a symmetric hyperbolic system, or you can write them in divergence form. Neither of these forms will be the form that are useful for what I want to do. I'm going to restrict to the positive density regime. I'm going to stay away from the free boundary problem because that's got its own degeneracies. I don't really want to deal with those while dealing with shocks at the same time. And to close the system, you need to pick an equation of state in which the pressure is a function of the density and the entropy. You need to choose such an equation of state, even to get the equations into this form. And so what I'm going to talk about works for essentially any equation of state where the speed of sound c, defined as such, is positive. This is the only requirement. I should say in passing that there's one exceptional equation of state that's very famous and corresponds to to bleaching gas. And for that equation of state, you do not expect shocks to form. Okay, but for every other equation of state, what I'm going to say essentially applies. Okay, now there are two kinds of propagation phenomena in fluid flow. There are sound waves and the transporting of vorticity and entropy. And you cannot easily see these phenomena from the way the equations are usually written. So later in the talk, I'll show you a different way of writing the equations, which goes back to my work with Jonathan. And in that way of writing things, those two phenomena become very explicit. And there's some very interesting structures in the equations that are important for what we do. All right, so let me just quickly say something about 1D theory. And in 1D, a lot is known. Mostly because the equations are at least locally well posed for initial data in bounded variation class. And for small bounded variation data, there is essentially a global theory, not just for compressible fluids, but for many systems. And that theory kind of buries all the interesting interactions into the function space. So you can prove things about the solution without really having to zoom in on the detailed structures. And that theory in particular accommodates the formation of singularities and the subsequent weak evolution. This is a huge field. I cannot possibly do it justice. There are many, many names that belong up here. I just put some of the more well-known ones. I put this result of Jensen from 2000. I think this is a very interesting result. This is an example of a paper. This is for a system with 3 unknowns, where this paper definitively shows that if you have large BV norm, then the BV norm, or sorry, large BV data, then the BV norm can blow up. The point being that even in 1D, it's not the case that all solutions are understood. The large data regime is still not understood for many systems in 1D. Okay, so my talk does and the result does connect to these 1D solutions, and I want to spend some time talking a little bit about the 1D theory because you can really get your hands on it. And I'll post these slides. There are some at the very end of the talk. So this is, or the very end of these slides, there's some extra slides on Berger's equation, which I won't really go through in this talk, but in those extra slides, I go through the analysis for Berger's equation in very complete detail. So you can really, for anyone who wants to learn more, you can click through these slides and really see things done explicitly for Berger's equation.
Maybe before you post the slide, you can remove the apostrophe.
Oh yeah, Berger. Yeah, that's right. Yeah, that's right. Oops. Yeah, I know this. That's right, Berger.
We don't like burgers. Maybe not yet.
No, I know this fact very well. Yeah, I know he personally. Yeah, he's made a remark about this actually. Yeah, I read something in print. He's like, I can tolerate certain slaughtering of my name, but not that one. So. Okay, so back to Euler. In one space dimension, you can introduce the Riemann invariants. These were the same quantities that Riemann introduced in 1860. And you can write the equations as a coupled system of quasi-linear transport equations, where the Riemann invariants R plus and R minus are determined in terms of the velocity and some function of the density, capital F, where F is determined by the equation of state. Doesn't really matter for purposes of this talk, the details. And the null vectors, the characteristic vectors L and L bar are determined explicitly. So this is a huge simplification in 1D. In multi-dimensions, you do not have a explicit way of determining the characteristics in terms of the fluid solution only. Okay, and so then a special class of solutions among these are the simple waves. And simple waves are such that one of the Riemann invariants completely vanishes. And for me, the one that vanishes will be R minus. So the interesting dynamics are all tied to R plus. Okay, and for such a system, or this reduces such a single scalar equation, you can study the phenomenon of shock formation using essentially the same analysis you would do for Berger's equation. Okay, so I just put in this yellow box exactly what I just said. For simple waves, the shock formation mechanism for that scalar equation is just like for Berger's. You take one x derivative of the equation and you get a Riccati type term on the right hand side. And that's one way to think about the source of the singularity formation is from this Riccati type structure. Now this picture is maybe a little too crude for what I want to do. So now I'm going to talk about singularity formation in more detail for 1D Euler. Okay, so the regime that I'm going to focus on today is what I will call a non-degenerate regime. So I'll say in more detail what that means. But in this non-degenerate regime, the shock formation will be stable. And so by stable, I mean qualitatively stable. All of the features that I will show you in my picture are stable. And if one way to think about the non-degeneracy in the context of Burgers is that at the minimums of the x derivative of the initial data, so at these minimums, these will correspond to singular points in the flow for Burgers' equation. The third derivative of the initial data should be strictly positive. And so later in my picture, I'll return to this non-degeneracy condition. This is not satisfied by all solutions, certainly. Okay. We call this transversal convexity for reasons that connect to the pictures that I'll show you. Now, there's something very different about fluid equations compared to Burgers' equations. And that's the presence of a second speed of propagation. In Burgers, there's only one transport direction. In fluids, there's two, L and L bar. And the second direction gives you leads to the formation of Cauchy horizons, which is not something you see in Burgers. And there's something nice about Cauchy horizons, which is that they can, in a sense, rescue uniqueness of classical solutions. So I'll show you in the picture what I mean by this. Okay, and everything I'm going to talk about so far is only understood locally in space, and so far only in this regime with transversal convexity. If you want to think of model initial data for Burgers, that corresponds to the regime I'm talking about. Consider initial data for psi, which is simply minus x plus x cubed.
I have to say that, yeah, I know what you mean, but that sentence is extremely counterintuitive. Cauchy horizons rescue uniqueness of classical.
Yeah, exactly. Yeah. We'll see. Well, maybe we can debate the language in a moment. See if Burgers. Right? Okay.
Burgers the better.
So here's the picture. So in this so what is the regime in this picture? So this is a regime where you perturb off of a simple solution, which is non-degenerate in the sense that I mentioned on the slide. Okay, so there's a lot going on in this picture, so I will start to go through it. So what we see on this red curve, B, which I will call the singular boundary, is the collapse of the characteristics corresponding to the L direction. And so these characteristics, which are these purplish lines in this picture, they pile up along the singular boundary in a very interesting fashion. So they pile up in such a way so that they're all tangent to the singular boundary. And they don't actually intersect along the singular boundary. The density of these straight line characteristics it goes to infinity, but they never actually intersect on the singular boundary. So if you want the map from down here to up here along the singular boundary it's a homeomorphism, though it's not a diffeomorphism along the singular boundary. And what you find is for the fluids is just as in the Burgers picture that along the singular curve, the x derivative of r plus blows up, just like as in Burgers' equation. Okay, now this lowest point here on the singular curve, we call it the crease because in higher dimensions, the analog of this cusp point has the appearance of a crease. You'll see it in the picture. Okay, now if you're interested in globally hyperbolic regions, because you're interested in constructing the maximal globally hyperbolic development, then once you have a singularity, you have to remove essentially the future cone of that point, at least remove the future cone of that point from the space-time. And what you see purple, dark purple curve is the Cauchy horizon. This is an integral curve of L bar, the other direction, which is I haven't shown any integral curves of L bar in this picture. And it turns out that the solution remains completely regular along the Cauchy horizon. So you can think that the data for the other Riemann invariant R minus is so small that variable has not had time to form any singularity up here. And on the other hand, the L characteristics, you can see from the picture, they haven't had time to collapse yet. The characteristics emanating from over here, they crash into this Cauchy horizon before their density has a chance to become infinite. Okay, so the solution ends up being if you have C infinity data down here, the solution is C infinity up here, except for at this cusp point and along this singular red curve. Okay, so let me contrast with Berger's equation. Or if you want, equivalently, let's forget about R minus. Let's take initial data where R minus is 0 and forget about the L bar direction. So there's only R plus and there's only L. Then for the non-degenerate initial data of the type that I mentioned earlier, modeled by minus x plus x cubed. If you look at the part of the flow that emanates from the data on this part of the initial data axis, if you were to continue, so there's no more L bar, so there's no more Cauchy horizon. If you were to continue the solution, you could continue following these characteristics, and they would pile up and form infinite density on this dotted pink curve. Okay, so for Berger's equation, you would see a singularity on this red curve, and you would also see a different singularity along this pink curve coming from the part of the initial data that comes over here. And so here, I'm calling this a fictitious singularity because precisely because the Cauchy horizon in the context of fluid mechanics is blocking this family from intersecting over here. If you were just studying Berger's equation or the one-speed fluid equation, then you would be grappling with the issue of non-uniqueness of classical solutions over here. So if you look at a point on this dotted curve, this fictitious singularity, and you ask, what is the solution at this point? You have no way of uniquely determining that from the initial data. There's no notion of there's no natural notion of globally hyperbolic for a one-speed system like Berger's. So if you're at this point and you say, what is the solution? On the one hand, you could say, well, the solution blows up because of the portion of the solution from over here on the left, or you could say it's regular because of the portion of the solution down here. These characteristics haven't had time to collapse yet by the time they touch this dotted curve. And there's no way around that uniqueness. So it's in this sense that the Cauchy horizon can actually rescue uniqueness of classical solutions in globally hyperbolic worlds. Okay, so this is the picture in 1D, and you can maybe with the help of the extra slides on Berger's equation, you could really, if you wanted to, you could really go through this in detail and in the course of an afternoon really understand this picture thoroughly. And I think it's a very illuminating exercise for anyone interested in this subject. So most of the rest of the talk will be about perturbing this picture away from these solutions and understanding what happens in 3D. So let me say a little bit about multi-dimensions. Again, there's a lot to say here, and I don't really have time to do the subject justice. But let me start with this well-known result of Rauch, which is that in multi-dimensions, unless there's very special algebraic structure in the system, it's going to be ill-posed in BV. And in particular, the equations of fluid mechanics do not have the good algebraic structure. So the equations are ill-posed. So that means you can't use any of the 1D BV theory. And so,
Sorry,
yeah.
I don't know actually what any of these words mean. So what does it mean for BV data in multi-dimensions?
Yeah, so I guess there are various ways of setting up the definition of bounded variation initial data.
It's BV in one direction or multi-variable?
Multivariable notion of BV, or there's no known analog of multi-dimensional BV for which one has well posedness.
What does it mean ill-posed in this setting? What fails?
So I think in Rauch's paper, it's seen at the level of rapidly growing Fourier modes. I'm not I'm not I'll have to take a look and remind myself of the exact statement of ill-posedness. But I'll send you the paper, or I'll look and we can talk. But I mean, the basic statement is like, given all the natural attempts at generalizing the definition of a BV norm, you can definitively prove that there exists such initial data in that space so that you can't propagate the solution in that space. Okay, so because of lack of a good notion of BV norm where you can propagate the regularity of the data, the modern approach to the study of shock waves in multi-dimensions, which I would say started in the late 1990s with work of Alinac. The modern approach involves really taking a detailed look at all the structures in the flow. So instead of trying to bury the difficulties in the function spaces, people are really zooming in on all of the different structures that can arise. And I mean, geometry certainly plays a big role in 1D analysis, a la the method of characteristics, but it seems to play an even more fundamental role in multi-dimensions. And in particular, as we all know, there's there's no getting around energy estimates in multi-dimensions. And this leads to some big technical complications in the context of shock waves, because at the end of the day, we encounter singular energy estimates. So, and I'll say just a little bit about this. Okay, so there have been a lot of contributions to the theory of multi-dimensional shock waves and other kinds of singularities for fluid flow. Many interesting developments. I mean, there's the very well-known work of Maida from the 80s, where he put he considered initial data that are discontinuous across a hypersurface, and he constructed a local weak solution. That's called the shock front problem. So for the shock front problem, the initial data are already discontinuous. Alinac was the first to study multi-dimensional shock formation for a quasi-linear multi-D system. So he did it for wave equations. Christodoulou famously studied the problem of irrotational shock formation in relativistic fluid mechanics in his 2007 monograph. And his big breakthrough there was importing ideas from mathematical relativity that allow you to construct portions of the maximal development. So really what Alinac did was follow the solution to the first singular time. And what Christodoulou gave us was a very sharp regularity theory that allows you to access portions of the maximal development. And in 2019, this is where he solved the problem I mentioned earlier, this restricted shock development problem. So a local in time weak solution through the shock for the caricature of the Euler equations that he cooked up, this irrotational model. And other kinds of singularities besides shocks have been studied. There's this the beautiful work of Merrill, Raphael, Radnyansky, and Sheftel, where they constructed implosion singularities where the initial data are C infinity and the density blows up in finite time. So in a shock, the density remains bounded. It's the gradient that blows up. In this work, it's the density that blows up in finite time. So that's a very different regime. A key takeaway is that, there are multiple kinds of singularities present in fluid flow. Igor and Dan have worked on global shock front type problems, constructing global solutions, global weak solutions to perturbations of spherically symmetric wave equation solutions. So is this accurate? Is it preprint form? And there's been some very interesting work by Luo and Yu on the construction of rarefaction waves in two space dimensions. So this is a sharpening of something that Alinac did earlier. They have a sharpened regularity theory. And then we'll hear from Jonathan Luke at the end of the conference. We'll hear about shocks for Einstein-Euler. That's a very interesting direction. Okay, and so what we've done with the Brescia, again, we've looked at open sets of initial data around one of these simple isentropic plane symmetric solutions. And we've given a complete description of the singular set and the Cauchy horizon in a compact subset of spacetime. So a complete description in a neighborhood of the set that we call the crease. Okay, so here's the picture. I'm just going to show. So this is a 3D. I'm not going to explain at this point in the talk. I'm not going to explain all of the things on the slide. I just wanted to show you the picture. This is simply a multi-dimensional analog of the 1D picture that I showed to you earlier. We did, for convenience, choose to put the perturbations away from symmetry, the x2 and x3 directions. We chose for convenience to let them live on the 2 torus, but we could have just as well done the case of R2. I guess this is a hyperbolic problem. There's finite speed of propagation, so you can locally study it. T2 allows you to avoid some boundary terms in some energy identities, and it just simplified our life. Okay, so this is the picture that I want to explain. What we did is we put smooth initial data on sigma 0 that are perturbations of one of these plane symmetric solutions where the perturbations live in some high order Sobolev space. We need a lot of derivatives to close the problem. The number of derivatives we need is anisotropic. This is the difficulty of needing lots of derivatives has been present in all of the works on shock formation in multi-dimensions that I'm familiar with. And so basically, the statement is that from such smooth initial data, there evolves a solution that is smooth all the way up to and including this Cauchy horizon C bar. And a singularity forms along this crease, this past boundary of the singular boundary B. And the certain derivatives of certain fluid variables blow up along the singular boundary B. And the solution is smooth all the way up to B. Now this hypersurface that's called K in this picture, this corresponds to the open problem that I called the shock development problem earlier. So what is K? So K is a codimension 1 hypersurface that, like the singular boundary in Cauchy horizon, should emanate from the crease. And it is tangent to this formally from Taylor expansions, or rigorously in the case of solutions with symmetry. One can see that K is expected to be tangent to the singular boundary. As it turns out, both K and B near the crease are sort of asymptotically null in a sense. In fact, B is literally ruled in a degenerate sense by null vectors. If I have time at the end of the talk, I will talk about that degeneracy because it's very interesting, but sort of skeptical about whether I'll have time to get into that. Okay, so let me try to give a condensed version of the story. If you insist only on classical solutions, there is no K. K does not belong in this picture, and the correct notion of maximal globally hyperbolic development has nothing to do with K. You follow the solution up to the Cauchy horizon where everything remains regular. You follow the solution up to the singular boundary where certain gradients blow up, and that's the end of the story locally. However, if you impose the standard weak formulation of the flow based on writing the equations in divergence form and insisting that the equations hold in a weak sense via integration by parts, if you impose such a formulation of the flow, that formulation agrees with the classical solution down here in the regular region. But as soon as you come to a neighborhood of the crease, the two formulations of the flow actually disagree. They predict different things. And the reason is that the weak formulation secretly has another speed built into it. It is the speed of the hypersurface K of this continuity. Okay, so by introducing the weak formulation, you're actually introducing a new propagation speed into the problem. And so, you know, that changes the solution. So in the shaded region in between K and B, in this shaded region, the classical solution will disagree with the weak solution, precisely because of this hypersurface K jutting out into the maximal globally hyperbolic classical development. So once the shock development problem is solved, what will happen is that the density and certain components of the velocity will actually jump across K. The jump will be 0 down here at the crease, and the jump will increase as you head up along K in a sort of very quantitatively sharply defined fashion. So you might ask, okay, if ultimately you're interested in maybe a global theory that accommodates the formation of shocks, and you know that such theory will involve weak solutions, you know, that means that the classical solution in the shaded region is not the right picture. It's not the right solution. So why did you construct it? And the answer is that a fruitful approach to the study of the shock development problem, that is a fruitful approach to actually constructing the weak solution, as shown by Christodoulou in the restricted problem, a fruitful approach is to actually start with the maximal classical development as your initial data for the shock development problem. So the Cauchy horizon, C bar, and the crease are part of the maximal classical development, and they're part of the weak solution. And in the construction of the weak solution, it is very convenient to have the singular boundary available as a mathematical barrier for the iteration procedure that one uses to construct the shock hypersurface K. So even though the classical solution in this region is not physically the solution that you care about, it is mathematically very helpful for solving the problem that one actually wants to solve one day. Okay, so this is the picture, and in the rest of the talk, I will spend some time setting up little pieces of the geometry that I need to explain features of this picture and a little bit about how the proof works. And I hope to have time to focus more on the Cauchy horizon, because I've talked about in other settings, I've talked about the singular boundary a bit more. And so the Cauchy horizon is sort of, maybe for many of you, the newer thing. Okay, so now to the geometry. So let me introduce some basic geometric notions in compressible fluid mechanics. So this material derivative vector field B appears all over the place. It's the convective derivative. And another geometric object that plays a fundamental role is the acoustical metric, which you can explicitly write here. Where does this metric? So this is the correct metric that governs the true nonlinear propagation of sound waves. So how do you find this metric? Well, at the most basic level, if you take the compressible Euler equations and you go to the irrotational class and you linearize the equations and you say, I want to find sound waves, and I want to see sound waves inside fluid flow, you will find this metric. So that's like the most crude hands-on way to think about where this metric comes from. Equivalently, if you go to irrotational class and you introduce a fluid potential and you write down the wave equation for the fluid potential, you will discover this metric. This is exactly the metric that will come up. Okay, so this is a really important geometric object, and it's a very fortunate and important fact for the theory that this vector field B, as measured by the metric G, is time-like. And what this means in practice is that if you have a hypersurface that is null with respect to this metric, and you look at the vector field B along such null hypersurface, it will be transversal. It will be because it cannot be tangent because B is time-like and the surface is null. And so from the perspective of PDE analysis, when you study the flow, there are solutions that solve wave equations. There are other variables that solve transport equations. And the transport variables, they think that null hypersurfaces are just the same as ordinary Cauchy hypersurfaces. So basically, when you're doing estimates for transported variables, they don't see any big difference between constant time surfaces and null hypersurfaces, and that ends up being really important for the regularity theory. Okay. So here's one example of techniques from relativity influencing fluid mechanics, the use of an iconal function to study the flow. So this is, if you want, simply the method of characteristics in multi-dimensions. And Alinac was the first to introduce this into the context of multi-dimensions in the context of shock formation. So basically, Alinac was the first to use iconal functions to really follow the solution all the way to a singularity. And these iconal functions played a fundamental role in Christodoulou's work as well. They certainly play a fundamental role in what I'm doing with Leo. And the initial data are chosen to be minus x1. And for the shock formation problem, the study of the flow seems to be a little bit insensitive to the precise choice of initial conditions for this for U. So I'm choosing the initial conditions for U to be exactly plane symmetric, even though the solution does not have to be exactly plane symmetric, and I'm able to get away with this at time 0 because there's quite a bit of freedom in constructing U. Okay, the level sets of the iconal function, I call them P sub U, or P sub U sub super T if you truncate them at time t, and these are characteristics. Once you have an iconal function, you can replace the Cartesian x1 with U, and you can use this system of 4 functions as a coordinate system. And I refer to this as geometric coordinates. Using this kind of coordinate system is exactly what Alinac and Christodoulou were doing. And the upshot is, in this coordinate system, the solution will appear to be rather smooth. So this is basically the method of straightening out the characteristics. And if you work with such a coordinate system, the advantage is that it essentially regularizes the problem. And you pay a bit of a price when you go to do energy estimates, because as it turns out, we don't know how to completely get rid of the singularity, even in this good coordinate system in multi-dimensions in the context of energy estimates. So at the end of the day, even though we straighten out the characteristics, the top order energies can be very degenerate. And that's a kind of annoying technical feature of the problem. I'm not going to talk much about it. Okay, so once you've constructed the iconal function, you can introduce what Christodoulou called the inverse foliation density. It's defined here. And so in the regime what we're considering, this quantity mu is initially approximately 1. And mu equals 0 is basically what signifies a shock. So that singular surface that I showed you, the singular boundary B, is a portion of the level set mu equals 0. And the claim is that mu geometrically can be thought of as the inverse of the foliation density of the characteristics. So put differently, if the characteristics pile up, in other words, if you think of U as a function of the Cartesian coordinates and the level sets of U pile up, that's essentially the same as the gradient of U, the Cartesian gradient of U blowing up. And that's essentially the same as this denominator going to infinity. And that's essentially the same as mu going to 0. So the piling, the infinite density of the characteristics essentially coincides with mu going to 0. Okay, so the study of shocks is in large the study of mu going to zero. There is another way to think about mu as a metric coefficient in the geometric coordinate system. It happens to represent a null lapse for some characteristic vector fields relative to the acoustical metric G. So there are many interpretations of mu. From the point of view of PDE analysis, it plays the role of a weight, a very important weight in the problem. Okay, so this is something I said earlier, the big idea of Alionak and Christodoulou, certainly motivated by many results from one space dimension, is that the solution remains rather smooth. And so another way that one can understand the significance of mu in this problem is if you write down the change of variables to go from Cartesian derivatives d alpha to derivatives with respect to the geometric coordinates, what you will find is that the coefficient of ddu degenerates. So in other words, from this formula, it's sort of quite evident how the u, t, x2 and x3 derivatives of something can remain bounded, while the d alpha derivatives blow up when mu goes to zero. So if, for example, if ddu something is order 1 and mu goes to 0, you can easily see that the Cartesian derivatives can blow up. And in fact, this is kind of how the proof of gradient blow up works. You do all of the hard analysis in geometric coordinates, and then at the end of the day, you recover the blow up of the Cartesian gradient from a formula like this. Okay. All right. And so here's just a picture of the characteristics achieving infinite density along a portion of the level set mu equals 0. So it turns out that in this language, one can exactly characterize the physically relevant portion of the singular boundary. So the physically relevant portion corresponds to the subset of the level set mu equals 0, where the u derivative of mu is non-negative. And so there's some very interesting characteristic geometry and causal analysis that goes into understanding exactly why this is the right portion of mu equals 0 that's physically relevant. I don't have time to get into those details, but I can tell you that the other portion of mu equals 0, which is the portion where the u derivative of mu is positive, corresponds to the fictitious portion of the singular boundary that I drew in dotted lines in the 1D picture. Let me also mention that so this is a picture in the Cartesian coordinates. If you set up the analysis in the geometric coordinates and you looked at the causal character of the other portion of the singular boundary where ddu of mu is positive, you would find that formally in that other coordinate system, the geometric coordinate system, formally that portion of the singular boundary has the character of a time-like surface. So you can't even expect to do estimates up to that surface portion because of its time-like character. So there are multiple ways of thinking about why this is the physically correct notion of the portion of the singular boundary that you care about. And then I didn't write it, but down here, the crease is exactly the intersection of mu equals 0 with ddu of mu equals 0. And in the regime that we understand, those two submanifolds, those two level sets, mu equals 0 and ddu of mu equals 0, they intersect transversally precisely in this crease. So the regime of transversal convexity or non-degeneracy that I mentioned earlier is also the regime in which those two surfaces intersect transversally. And you can easily cook up initial data where they do not intersect transversally. And then the picture can dramatically qualitatively change. In such a worse regime, you can have a situation where a whole family, a whole open family of characteristics piles up on a single codimension 2 manifold. Or in the 1D picture, you can have a continuum of characteristic lines pile up at a single point. That's a much more degenerate regime, and much less is understood in multi-dimensions about that regime. Now, certainly this picture with Leo that I'm constructing is not understood in that regime. Okay, so let me say something about regimes. So there is a regime of solutions that's a little easier to study. And this is the regime that was first studied by Alanak. This is the regime where the singular boundary and the crease enjoy some convexity. And in such a regime, for example, there's a unique lowest point on the singular boundary. And you can think that many of the prior works, so Alinak's, there's another approach to shock formation by Buckmaster, Scholar, and Vikol that goes through self-similarity and modulation parameters. And those approaches are sort of somehow centered around the lowest point on the singular boundary, which granted is not known in advance. But in such a regime, you can sort of you can touch the unique lowest point with flat sigma t foliations. If you think of doing sort of estimates using flat sigma t foliations, you can imagine that you set the problem up so you just the flow stops as soon as you touch the lowest point on the singular boundary. And that's how you can follow the solution to the lowest point. And then if you tilt a little bit those planes, those flat sigma t's, you tilt them a little bit in such a way that they remain space-like, and you do the analysis relative to that slightly tilted foliation, then you can touch another point on the crease, and so on and so forth. And in such a way, you can, in principle, construct the entire crease in the regime where you have this kind of convexity. And the problem I'm looking at with Leo, we do not have that kind of convexity because we're perturbing off symmetric solutions. And so we construct different foliations that are precisely adapted to the shape of the singular boundary. And I will show some pictures, but I won't have time to get into the construction of the foliations. Okay, so what we are really after is a set of techniques that allows us to study large portions of the solution across space and across time. And so that basically forces us to introduce techniques that can handle situations where you don't have convexity. Okay, so let me just say a little bit more about geometry. Once you have constructed the Iaconal function, you can construct vector field frames that are adapted to the flow. So this is done in many problems in mathematical relativity, and you can do it in fluid mechanics as well. You can construct the gradient geodesic vector field LGO. You can multiply LGO by mu to get something called L. And this is the correct analog of the L that I explicitly wrote in one space dimension. This is the multidimensional analog. If you normalize the geodesic vector field by mu, you get something so that if you apply it to T, you get 1, which is exactly what occurred for the explicit vector field that I called L in 1D. And so this is a good vector field to work with. Okay. And you can, building off of L, you can construct an entire frame of vector fields. There's a vector field called X, which is has length 1, and it's transversal to the characteristics, and it's orthogonal to the codimension 2 surfaces where you intersect the characteristics with sigma t. And then you can construct angular vector fields by using orthogonal projection of the Cartesian vector fields. And I'm not going to get into the details of the construction, but ultimately you end up with a good vector field frame called L. brev x and y. And so brev x is you take this order 1 vector field x and you multiply by mu. So this is, of these 4 elements of the frame, this is the one vector field that's transversal to the characteristics. And as you can imagine, a lot of the interesting analysis is tied to this brev x vector field. And another way to think about this is if you expect the solution to be singular, or its derivatives to be singular in the transversal directions, then what you're doing with brev x is you're precisely removing the singular behavior by multiplying by the correct weight. So in other words, basically the gradient of the solution is going to blow up like 1 over mu, and you're multiplying by mu and working with a mu weighted thing to remove the degeneracy. That's essentially what's going on here. Okay, and as I've said, so basically deriving regular estimates with respect to this frame is essentially equivalent to proving that the solution is smooth in the geometric coordinate system. So let me just, I mentioned this technical difficulty with the high order energies. I'm not going to discuss this in detail. Let me just show you the picture. These are the characteristics coming close together. This is the vector field called brev x, which is mu times x. It's transversal to the characteristics, and as mu shrinks, mu times x looks small in the picture. Vector field y is tangent to the characteristics. Vector field L is null and tangent to the characteristics. So this is kind of how the good fruitful setup for the PDE analysis. Okay. So now I can finally say something about in more detail about what I actually did with Leo. So fix one of these simple isentropic shock forming let me call it a background solutions. One of these 1D solutions that I showed earlier in the talk, and consider only initial data that satisfies this transversal convexity condition where the second derivative of mu with respect to u along the singular boundary is positive. So this notion of transversal convexity coincides with the non-degeneracy that I mentioned for Berger's equation, the thing that's modeled by Berger's data with minus x plus x cubed. Okay. Then the conclusion is that the whole picture, the shock formation, everything else along with it, is locally stable under general perturbations of the initial data, where you can have vorticity and entropy in the perturbations, even though you don't have vorticity or entropy in the background solutions. And so the first paper we've posted, which is where we basically construct all of the singular, or a large portion of the singular boundary that includes the crease. And we're writing up the Cauchy horizon paper. Okay, so for reasons that I hope to show in pictures, the two problems seem to require different techniques. Okay, and so put the two things together and we get an interesting portion of the maximal globally hyperbolic development. Now, it turns out, I think it's fair to say that uniqueness of the maximal globally hyperbolic development is open. So this is something that maybe can talk to Jan about later. But basically, to conclude uniqueness of the MGHD, as far as I know, you need global information across space. And right now we have only local information. So I actually don't know of any regime in fluid mechanics where there's an open set of initial data where uniqueness of the MGHD has been shown.
Can you show existence of an MGHD?
So so there's probably a regime where this can be done, but you need assumptions. You'll need something like, or at least I would need something like this globally in space.
Just to show existence of an.
Right, because for example, if you have the situation that I mentioned a few minutes ago, where you have a continuum, let's say in the 1D picture, you have a continuum of characteristics collapsing into a single point. I don't know how to construct the Cauchy horizon in multi-dimensions, for example. At least things become very degenerate. So if you considered initial data with a profile, so there was some kind of monotonicity built into it, where you have some weak version of this all the way out to spatial infinity, then probably in that regime, one could construct a maximal development. And then in that case, I think uniqueness would fall out from essentially what Jan and Real and Epron did, because for such a picture, you would have, so I will try to quote words from your paper. The maximal development would live on one side of the boundary. You wouldn't have any kind of a hinting off type effect. And I think essentially that's sufficient for concluding uniqueness. But again, I don't know of any regime where that's been written down carefully. It's probably not completely trivial to do that. Okay, so this is the same picture from before. Okay, so I have 5 minutes left. Okay, so I will just I will show a few pictures and then say a little bit about the Cauchy horizon. So this is what we constructed in the first paper with Leo, which is posted. It's got the word singular boundary in the title if you wanted to look it up. Okay, so I'll be very schematic and terse because of time constraints. Smooth initial data are given down here, exactly of the type that I mentioned on the previous slide. For a long time, by Cauchy stability, nothing interesting happens. And then we start constructing these foliations by space-like hypersurfaces that are adapted to the precise shape of the singular boundary. So the construction of these foliations required a lot of effort on our part. I can't really hope to get into them. But so basically this lower piecewise defined, it is piecewise defined, looking foliation is the lowest member of the family. And then we follow the solution all the way up to the highest member of the family, which includes the upper slice includes exactly a portion of the singular boundary that I mentioned earlier, the portion corresponding to the U derivative of mu being non-negative. Okay, so this part of the flow, or this part of the development we constructed in our first paper. And I should mention that this is a picture in TU x2, x3 coordinates, so geometric coordinates. So now I want to say just a little bit about how we set up the problem of constructing the Cauchy horizon. So we have this picture. This is the vector field X that I introduced earlier. We want to construct a second iconal function called U bar. We want to construct it in such a way so that U bar equals 0 will be will include the Cauchy horizon. How do we do it? Step 1 is we want U bar equals to be 0 along the Cauchy horizon. So in particular along the crease, which because the Cauchy horizon emanates from the crease. So step 1 is to construct initial data for U bar along this portion of this upper space-like looking slice up here. And we do that. So the initial data for U bar, we construct it by solving a transport equation for U bar. So basically the x brev derivative of U bar will be equal to something. And that gives us initial data for the other iconal function U bar on this slice. And then we solve the iconal equation for U bar backwards down here in the region where we've already constructed the solution. So maybe in particular, the transport equation for U bar is that it's x derivative of U bar is equal to minus mu. U bar is initialized to be 0 along the crease, like I said, and then you can show that U bar on that little space-like slice behaves kind of like behaves like U cubed, where U is the geometric U, and yeah, so I don't have time to get into these technical details. This is exactly what I said. You propagate the iconal equation, and there's an interesting degeneracy that appears in the equation, which is that the second, even in the good coordinate system, the second derivative of U bar in the L direction seems to be infinite at the crease due to this kind of behavior. So in this caricature, the crease corresponds to t equals 1 and u equals 0. And if you, this is all raised to the power of 1/3. So if you take another derivative of this, an L derivative, remembering that LT is 1, if you put u and t to 1 and u to 0, you'll get to infinity. So this is the degeneracy that one has to deal with. I think it's a real degeneracy, and fortunately, this never comes up in the PDE analysis. That's sort of something to you. Okay, so here's the picture. This will be the last the last part of the result that I talk about. I'll just show you a little bit about what we're doing. So this is now a picture in Cartesian space, as opposed to the previous picture, which was in geometric coordinate space. Okay, so in the previous paper, we followed the solution up to here, and we constructed initial data for U bar, and then we solved down here for U bar. This ends up being, even solving for U bar, the new Icoma function ends up being a bit of a non-trivial problem, because the Icoma equation sees some remnant of the degeneracy of the shock. So it's actually a degenerate, fully nonlinear transport equation that you have to solve to construct U bar. Okay, and then so the level sets of U bar are these, let me call them ingoing null hypersurfaces. And you construct U bar first in the region where you've already understood the solution from the first paper. And in particular, because we already know the solution down here, we have information about the solution on some level set of U bar over here in the region where everything is expected to remain regular, because the singularity is expected to be, only on the singular boundary and some remnant of so over here, there's no singularity. That's probably the simplest thing to say. And then we have the level sets of U, which are the, so the dotted stuff is you can think of them as initial data surfaces, initial data in the sense that you already know the solution in this region. And then we study the characteristic initial value problem for the fluid equations on characteristic diamonds. So basically we redo the shock formation problem in the context of characteristic initial value problems for fluid flow to understand the solution in these characteristic diamonds. And the whole setup has been such that U bar equals 0 is exactly the Cauchy horizon. So that's a very brief feel for the kinds of analysis we do. So I won't talk about anything else, any other aspect of the result. Let me just say that there are some very interesting directions. As I mentioned, the shock development problem in full generality is completely opened. Once that problem has been solved, we'd of course like to look at the long time behavior of solutions. The shock development problem is local in time. Ultimately, we want to understand things globally in time and space. This will involve studying the long time behavior of vorticity. A member of the audience appears unhappy.
Time behavior of vorticity is that it blows up. And then this has nothing to do with compressible canal.
Well, there may be regimes that are accessible that, it's not understood. Well, possibly 2D is a little simpler.
Wow. Okay, that's apropos of nothing, right?
Another interesting problem, there's been work on this recently by Sanchez and Colgram, is to study zero viscosity limits and to try to understand the behavior of the limits in high norms. So a classical result is to understand zero viscosity limits and L1 norms in space, but this new result for Burgers is giving much more information up to the time of first blow up. And then similar problems for multi-dimensional or multi-speed systems are most of shock formation for more interesting and more complicated systems is essentially open, except we'll hear from Jonathan at the end of the talk on Einstein Euler. Okay, so I will stop there.